Greetings, everyone. Today, I will be discussing the relationship between conservative forces and potential energy. But before I start, let me introduce myself. I am Jasmine Melrose Villa from CED 10301P. So, we have the equation for conservative force. Okay. First, we have this equation and we can associate a potential energy for a system with a force acting between a members of a system, but we can do so only if the force is conservative. In general, the work sub internal done by a conservative force on an object that is a member of a system as the system changes from one configuration to another is equal to the initial value of the potential energy of the system minus the final value. So, this is the formula. So, while in the equation for non-conservative forces, we have this formula, and now, what is the relationship of these two? In the preceding section, we can found that the work done on a member of a system by a conservative force between the members of the system does not depend on the path taken by a moving member. The work depends only on the initial and final coordinates. For such a system, we can now define a potential energy function such that work done within the system by the conservative force equals to the negative of the change in the potential energy of the system. Let us imagine a particles in which a conservative force displacement acts between the particles. Imagine also that the configuration of the system changes due to the motion of one particle along the x-axis. The work done by a force displacement as the particle moves along the x-axis is this one, where F sub of x is the component of the displacement of force in the direction of displacement. That is, the work done by conservative force acting between members of a system equals to the negative of the change in the potential energy of the system associated with the force when the system configuration changes. We can now express as this one. Therefore, the potential energy is negative when f of x and d of x are in the same direction, as when an object is lowered in a gravitational field or when a spring pushes an object toward to equilibrium. It is often convenient to establish some particular location of x sub I of the member of a system as representing a reference configuration and measures all potential energy differences with respect to it. We can define the potential energy function as this one. The value of potential energy is, the value of potential energy often take to zero reference configuration. It does not matter what value we assign to potential energy because any non-zero value merely shifts to u of x by a constant amount and only the change in potential energy is physically meaningful. If the point of application of the force undergoes an infinitesimal displacement of d of x, we can now express the infinitesimal change in potential energy of the system of d of u as this one. Okay. Therefore, the f of x, or the conservative force, is related to the potential energy through the relationship of this one. Now, in the case of the deformed spring, we can now substitute the value of its expression, then the final derivation is this, which corresponds to the restoring force in the spring or Hooke's law, because the gravitational potential energy functions of gravitational energy is equal to mass, and the G is equivalent to gravitational potential energy, and M is the mass of an object. Okay. So, ito. And it follows to the force, which is the 2 mg when we differentiate the potential energy with respect to y instead of x. We now see that the potential energy is an important function because a conservative force can be derived from it. So that's all. Thank you for listening. Again, I am Jasmine Melrose Villa.